find the equation of the line, we need a point on the line, so we could choose 0.14, and we also need to find the gradient of the line. To find the gradient of the line, if we use the gradient formula, m is equal to y2 minus y1 over x2 minus x1. Call one of these points x1, y1, and the other point x2, y2. And then we fit in the values, so that would be 4 minus minus 2, that's going to become plus 2, over 1 minus 3. 4 plus 2 is 6, over 1 minus 3 is minus 2, 6 divided by minus 2 is minus 3. So the gradient of this line is minus 3. If we then call our point AB, we use the formula y minus b equals m bracket x minus a. And we now fit our values into this. So that's y minus 4 is equal to negative 3 bracket x minus 1. And it's quite alright to leave our answer like this. We're asked to find the gradient of this line, and it makes a 72-degree angle with the positive x-axis. Now, to find the gradient of the line when we know this angle, all we need to do is to work out the tan of the angle, so the tan of 72 degrees. And tan 72 to three significant figures is 3.08. So we have a line L with the equation y is equal to 5x minus 4. The gradient of that line is given by this number in front of the x. A line that's parallel to L will have the same gradient. So the gradient of a line parallel to L will have the same gradient, m is equal to 5. A line that's perpendicular to L. Now perpendicular lines follow the rule that m1, m2 is equal to negative 1. So when we multiply the two gradients of two perpendicular lines, the answer is minus 1. Now, if one of these gradients is 5, we have to work out what we'll multiply by 5 to give minus 1. 5 times a fifth is plus 1, 5 times minus a fifth will give us minus 1. So the gradient of a line perpendicular to L will be m is equal to negative 1/5. So this is the graph of y is equal to f of x. And we're asked to draw the graph of y equals negative f of x. Y equals negative f of x means that all the y coordinates on this graph have to be multiplied by minus 1. Another way of looking at this is that this graph is reflected in the x-axis. The point negative 5, 0 will stay where it is. The origin will stay where it is. The point negative 3, 4 will reflect to the point negative 3, negative 4. And then we can draw the graph through these points. This will become a minimum and the origin will become a maximum. So this is the graph of y equals negative f of x. It's important to annotate the graph, to mark these points on the graph. The second graph we have to draw is y equals f of x plus 3 in brackets. Because the x plus 3 is in brackets, this tells us that there is a movement of this graph to the right or to the left, sideways. Plus 3 tells us to move the graph to the left by 3. So negative 5 will end up at negative 8. Negative 3, 4, move 3 to the left, will go to the point minus 6, 4. The origin will move to the point minus 3, 0. The graph will be the same shape, but just drawn through these points. So this is the graph of y is equal to f of x plus 3. In the equation y equals a to the x, we have to find the value of a. Now we know that 1, 9 is a point on y equals a to the x. So we know that when x is equal to 1, the y coordinate is 9. Fitting these values in, instead of y, 9 is equal to a to the x, which is a to the power 1. So 9 equals a to the power 1, so a is equal to 9. We've got the graph of y equals 8 to the power of x shown here. Its inverse function is shown here. Now the inverse function of y equals 8 to the power of x is y equals log to the base 8 of x. So f of x is equal to x to the power 5. Whatever is in the brackets is taken to the power of 5. G of x, whatever is in the brackets, is multiplied by 4, and then 3 is taken away from that. We have to obtain an expression for f of g of x. First thing we do is we put our g of x formula inside the brackets. So this is f of 4x minus 3. F takes whatever's in the brackets to the power of 5. So this is equal to 4x minus 3 to the power of 5. And this is our expression for f of g of x. Y is equal to 2 over x to the power of 5. Before we can find the y by dx, before we can differentiate, we need to rearrange this. You can't differentiate when there's a power on the bottom. So we bring the x to the 5 up to the top, and what happens is it becomes an x to the minus 5. 2x to the minus 5. Now we can differentiate. The y by dx is equal to, multiplying the minus 5 times the 2 is minus 10. The x power is then 1 is subtracted. So minus 5 minus 1 gives us minus 6. We could leave our answer like this, or we could write negative 10 and take the power of x back down to the bottom, but then it would be x to the power of 6. We're trying here to find the gradient of the tangent to this curve at the point P, 5, 3. The gradient of the tangent is given by dy by dx, and then we have to fit in the x value of 5. So the first thing we have to do is to differentiate y. Differentiating x squared gives us 2x. So dy by dx is equal to 2x. Differentiating minus 6x is minus 6. Differentiating 8 is 0. Dy by dx tells us the gradient of the tangent, or m tan, at any point in the curve. We're interested in the point where the x coordinate is 5. So we now have to fit this value, x equals 5, into this equation for finding the gradient of the tangent. So m tan is equal to, and we put x equals 5, 2 times 5 minus 6. 2 times 5 is 10, minus 6 is 4. So the gradient of the tangent at P is 4. We're asked to find the stationary points on this curve. Stationary points are found where dy by dx is equal to 0. So the first thing we need to do is to differentiate. Dy by dx, 1/3 x cubed, multiply the 3 times a third, which just gives us 1, x to the power 2, so just x squared. Differentiating minus 3x squared, 2 times minus 3 is minus 6, and the x goes down to the power of 1, just x. Differentiating 8x just gives us plus 8. Differentiating the minus 1 is 0. So dy by dx is equal to x squared minus 6x plus 8. Now stationary points are found where dy by dx is equal to 0. In other words, where x squared minus 6x plus 8 is equal to 0. Now this can be factorised, x and x, then two numbers multiplying to give 8, which combine to give minus 6x, so there'll have to be two negative numbers, minus 2, minus 4. X minus 2 times x minus 4 equals 0 tells us that x minus 2 could equal 0, or x minus 4 equals 0. This gives us that x could equal 2, or that x could equal 4. We now need to find the y coordinates for each of these x coordinates, so we need to fit these values into the original equation. Fitting x equals 2 in gives 1/3 times 2 cubed minus 3 times 2 squared plus 8 times 2 minus 1. 2 cubed is 8, so this is 8 over 3. Minus 3 times 4 is 12, plus 8 times 2 is 16, and minus 1 at the end. And this gives us 5 and 2/3. So our first stationary point is 2, 5 and 2/3. We then have to fit x equals 4 into the original equation. So y is equal to 1/3 times 4 cubed, so that is 64 over 3, minus 3 times 4 squared, 4 squared is 16, minus 3 times 16 is minus 48, plus 8 times 4, which is plus 32, and a minus 1 at the end. And this gives us that y is equal to 4 and 1/3, giving us our second stationary point, 4, 4 and 1/3. We now have to decide on the nature of these stationary points. To do that, we've got a nature table, and we're looking at values of x around 2 and also around 4. We then look at the sign of dy by dx, which then tells us about the curve's shape. Fitting in a value of 1 into the dy by dx formula will give 1 squared minus 6, which is minus 5, plus 8 is 3. So dy by dx is positive to the left of 2. At 2 we know that dy by dx is 0. For these two places we can choose a value of x equals 3 and put 3 into our dy by dx formula. 3 squared is 9, minus 6 times 3 is minus 18, and a plus 8 at the end. 9 and 8 is 17, minus 18 is minus 1, so dy by dx is negative for this position and for this position. At x equals 4 we know dy by dx is 0. Taking a value beyond 4, 5 for example, fitting that into dy by dx, 5 squared is 25, minus 6 times 5 is minus 30, with a plus 8 at the end. 25 minus 30 is minus 5, plus 8 is plus 3, so this is positive. So the shape of the graph around 2, positive gradient, 0, negative, negative gradients, 0, positive. So this tells us at x equals 2 we have a local maximum. So this is a maximum turning point. At x equals 4 we have a local minimum, so we would write that this is a minimum turning point. So we read through this first of all that a repair has been made to a small reservoir retaining wall. Unfortunately, water is able to seep through small gaps in it, and this causes 1/5 of the water in the reservoir to be steadily lost each day. To counteract this loss, 1,000 metre cubes of water are pumped back in each day. There are UN metre cubes of water in the reservoir at the start of a particular day. We're then asked to write down a recurrence relation for UN plus 1, the number of litres in the reservoir at the start of the next day. So, UN plus 1. Now, if 1/5 of the water is lost each day, that means 4/5 of the water is left. So we would multiply the previous day's amount by 4/5. So that would be 4/5 UN. We're told that to counteract the loss, 1,000 metre cubed of water are pumped back in each day. So we would then add 1,000. And this would tell us the amount in the reservoir the next day. This is the answer to part A. For part B, it says it is known that if the reservoir has more than 6,000 metre cubes of water, further damage will be caused to the retaining wall. And we're then asked to find the limit of this sequence as n tends to infinity. In the long run, the values of UN plus 1 and UN will be the same. So if we let L equal UN plus 1 equal UN in the recurrence relation formula, UN plus 1, L, is equal to 4/5 times L plus 1,000. This is 1L. So we now subtract the minus 4/5 from each side of the equation. So this is 1L minus 4/5 L, and this is equal to 1,000. 1L minus 4/5 L leaves us with just 1/5 L. So 1/5 of the limit is 1,000. So if we multiply both sides by 5, we'll get that L, the limit of this sequence, this recurrence relation, is 5,000. Now for part 2, it says in the long term, can the reservoir sustain the policy of pumping back 1,000 metre cubes each day? We're told that as long as there's no more than 6,000 metre cubes, no further damage will be caused to the retaining wall. Now, since this limit is less than 6,000, then we can say that in the long term, there will be no further damage.